Hello everybody. There is another example that we can do, and this example is concerned with the energy stored in a capacitor. So let's say we have two capacitors, and these two capacitors, as given by the problem, it says two identical capacitors. So they are exactly identical, which means that if that was empty and this one empty, they will have the same capacitance C0 for both of them. Okay, but except it says one is empty, so I'm going to assume this one is empty, and the other one is filled with a dielectric constant material. So there's a dielectric slab in this one, and kappa for this one is equal to 7. So if this was C0, we know that C is equal to kappa times C0. So basically, this is not C0 anymore. This is equal to 7C0, and that's what we need here, okay? So these two identical if they were what? Both empty, but one of them has 7 dielectric value constant. So it has 7 the capacitance of the other one, okay? All right, so the empty capacitor, this one, was connected to a 14-volt battery. So I'm going to connect it to a 14-volt battery here, as you can see. And what is the voltage across this one? So we want to know the voltage across this one. We don't know what that is. We want to know the voltage across that one such that both of their energies, the empty one and the filled one, are the same. Okay, how do we do this one? So we start actually from where the problem is. We need the energy of both of them to be the same. So I'm going to call this 1, and I'm going to call this 2. So I'm going to say energy of 1 must equal to energy of 2, because that's what the problem dictates. Okay. There is several forms of the energy of a capacitor for a capacitor. Several forms of the equations for the capacitor. Okay, so there are several forms of the equation that we can use for the energy of a capacitor. Which one is more appropriate here? It seems that we have the capacitance, and we have the voltage. I believe maybe we should use this equation in general, where energy is equal to 1/2 times CV squared. If it doesn't work, we can actually use another form if we need to. But let's try this one. Energy of 1 is basically equal to 1/2 C0, because it's empty, and the voltage V squared, okay? And then we know the voltage. And this must be equal to the energy of the filled one, which is 1/2. Now this C is equal to 7C0, and now what? We have the voltage, which is unknown, and that's square. Now this voltage, remember, I'm going to call this 2, and this is 1, just to distinguish the two from each other. Now the nice thing about 1/2, they go away. C0 and C0 go away. This one is what? 14 square, right? Now it's 14 is equal to 7 V2 square. So with some quick calculations, we can find that V2 is equal to the root square of 28 volt. Now let's look at the answer, because the answer is more important than the whole process itself. Why? I'll show you. Look, the voltage required to charge this guy up to an energy E1 is 14 volts. This one, it has a dielectric slab of 7, and it needs root square of 28 volts. Which one is bigger, 14 or root square of 28? As a matter of fact, 14 is much bigger. And that tells us why putting the slab means that we need a less battery power to charge this guy or to get it store the same energy we need for this one. And that's another benefit for dielectric slabs. Okay? Now, let's actually find the energy density of this one if the distance between its plates is 3 centimeters. All right? Okay. How do we do that? We know that the energy density is equal to 1/2 kappa epsilon 0 times the electric field square. All right? We know we don't have the electric field across the plates. We have the voltage, but we know that E is equal to V divided by D. All right? So let's plug in the numbers. 1/2 kappa is 7, right? So that's 7. Kappa is 7, right? Okay. And epsilon 0 is 8.85 times 10 to minus 12. You should be given this value. And it's in Coulomb square per Newton meter square. And E square is equal to V square, which is 28, divided by the distance, which is 0.03 square. We already squared the 28. We took out the square root here. Okay? After some calculation, we will get the energy density is equal to 9.64 times 10 to minus 7 joule, and this is energy density per volume, so joule per meters cube. And this is it. Thank you very much.